August of 2004, there was a 5-volt power supply that drives the mechanisms on STIS, and it failed. When that happened, it basically meant that STIS could not do science anymore.
STIS was our first black hole hunter. It confirmed for the first time the existence of a supermassive black hole in the center of a galaxy, and it went on to make the first detection and chemical analysis of the atmosphere of a planet around another star. We want to keep on doing that kind of work.
STIS is what's called a spectrograph. What it does is spreads the light out into its different wavelengths. That's really important if we want to learn about how fast an object is moving, what it's made of, what the pressure and temperature. It's getting at the physics of what's going on up there in the universe.
You might well ask, if we're going to fly a cosmic origin spectrograph that's the most sensitive spectrograph we've ever put on Hubble, why do we need to bother to repair the Space Telescope Imaging Spectrograph? Space Telescope Imaging Spectrograph can do a number of things that COS can't do, and conversely. Between the Cosmic Origin Spectrograph that's very fast and very efficient, and the Space Telescope Imaging Spectrograph that provides finer resolution and a smoother cut, as it were, through the light from a star or a galaxy, and you have a much more complete set of tools to use for a variety of purposes.
It was huge motivation to recover STIS. So our engineers embarked on one of these rapid development programs, and the STIS failure was very easily characterized. We knew exactly what happened, we knew exactly what card, we knew exactly what component. And the challenge became, can we get to it?
This particular activity that we're going to do to try to fix STIS wasn't meant to be done in space, it was meant to be done here on Earth in a clean room.
Now, since no one ever expected this to happen, when they sealed up this instrument, they sealed it up so it was nice and secure. In fact, there's 110 of these very small screws that we need to remove from the instrument in order to gain access to the board we need to replace.
And these screws are not what we call captive. In other words, as you take the screw out, it's loose. There's nothing holding it to the board. The engineers here at Goddard have been very creative in designing a cover plate that we can put on over top, that as we take the screws out, they'll be captured by this plexiglass cover.
We designed what's called the fastener capture plate. It attaches onto the instrument. It's got holes that the astronauts can access their tool into. They're small enough for the tool bit, but not large enough so the fastener can come out.
My job is going to be to drive each one of these screws, remove that plate, get inside of it, and then remove the board, much like you would remove a board in a computer in your house, except we're in these fancy clothes, a big fancy spacesuit, and we're using fancy tools to do it. We want to make sure we do it right.
If we are going to go do exploration and continue with on-orbit assembly and test a spacecraft, we got to learn how to do that. We got to learn how to pull boards out and put boards in. And so here we are, Hubble once again is the Pathfinder.